excited to have with us Mosharaf Chowdhury. He's the Morris Wellman Assistant Professor of Computer Science and Engineering at the University of Michigan, where he focuses on network-informed system design for big data and AI applications. He's perhaps best known as a co-creator of Apache Spark, and his artifacts run in data centers across the world. More recently, he has spearheaded a systems research in federated learning in the academic community, and we're excited to hear more about this in this talk. He will be speaking about system support for federated computation. Mosharaf, please take it away.
Thank you so much for inviting me and for the kind intro. I just want to make sure that everyone can see my slides and it's working.
Yeah, you're good.
Okay. So let's get started. I am from the University of Michigan, where we've been working on designing systems for analytics and machine learning. And we started in the cloud, and over the years, we have gone more and more distributed, and we ended up in this federated world. But before going there, I just want to start from the basics. What does it mean to have a software stack for learning and analytics? So we all have data somewhere, and then we want to learn something, training models, or we want to do some analysis. And even if we go back tens of years ago, many decades ago, there are two steps in the middle that always had to happen. We have to decide what we actually want to run, where do we want to run them, and then we also have to figure out exactly how we are going to run them, when we are going to run them. And this is only even for a single job, even without going into multi-tenancy. There are two sort of important layers that are between this application and wherever our data or storage is, that we have to be able to come up with a plan, and then we have to be able to execute that plan very well. So planning involves figuring out maybe the DAG you want to run, the data flow program you're going to run at the overall scale, but it could also be how you're in different parties. Similarly, the executions layer, it takes into account many constraints of where things are actually running, and then being able to execute all the code necessary wherever the data is located, being able to communicate, being able to orchestrate all this computation across sort of a distributed set of nodes or machines. And this very high level and oversimplified layering of software stacks for learning and analytics have basically remained the same going back 3, 4, 5 decades ago in the database community. Then we went into this big data and cloud, and we still were roughly doing the same thing. And when we moved from single server to a cluster of machines in the cloud, everything changed, but they also remained the same because the data center network was getting faster and faster with more bandwidth and lower latency. And we could sort of assume that data and execution are very close to each other and co-located. So as we started moving on to these multi-cloud or multi-silo scenarios, our data started to become distributed across sort of geo-distributed location and in multiple different silos and clouds and data centers. And between them, they have lower bandwidth than inside a data center and higher latency than inside a data center. Within each silo, they have everything or close to that, what we typically would have inside a cloud data center. And then we are moving to more interesting settings with cross-device federated learning and analytics, where we have even more devices. Each of them have some compute and some storage where they are maintaining their local private data. They have different capacity. They may be available at different times. And overall, it's a much larger scale and more uncertainty. But a common theme between or across both of these scenarios is that at the end of the day, network rules. It is very constrained. Bandwidth is very low. The latencies between different entities from the edges to the cloud, between the edges are very high. The topology of the network is hard to predict with many dynamic variations. It's asymmetric. much less reliable than what we have in the data center. And as a result, we had to, or rather we started to, rethink the entire software stack, assuming that our network is not going to be as nice as we have always had, the interconnect within a server or the data center network within a cloud. And in the last 4 or 5 years, we have done a bunch of work that spans all these layers in the context of cross-device and cross-silo federated learning and analytics. And today, I'm just going to focus on a couple of these works that focuses on execution layer and the planning layer. And I'm also, just to give some flavor of the different types of work and systems building research that we do, I'm going to pick 2 projects that are focusing on cross-silo, and then the other one is focusing on cross-device scenarios. And I'm going to end with providing, or rather introducing, this new project that we have started in the process of doing all these systems research in terms of how can we build this experimentation platform that is highly scalable with very large data set, very big models, and that's actually very challenging. So let's get started with the first one. So in this case, what we wanted to do, and we assumed that the data is distributed across multiple silos. Each of the silos have a lot of computation. They are just connected by very weak networks, slow networks. And by slow, I mean, unlike data center networks, the bandwidth between these silos can be gigabits or even lower, and the latency between them can be hundreds of milliseconds, maybe, or at least tens of milliseconds. And to understand why this latency and bandwidth variation and everything else remains the same, why just simply changing these 2 things affects existing frameworks, let's just take a walkthrough over a very simple example. So this is the typical model. You have a central coordinator who is in charge of coordinating all the work, and there are workers that are distributed in many different silos. And central coordinator, it has received a plan that it is trying to execute. So Sol is going to be an execution layer, and it's dispatching these tasks to the worker. Time is going down, and tasks get launched. These are computation tasks, and worker, it finishes, and then it updates the central coordinator that I'm done with whatever I'm working on, and then a new task gets launched. And because of the very high latency between wherever the worker is and where the central coordinator is, there is this big chunk of time where the worker is not necessarily doing anything. It's waiting for the central coordinator to give it more work to do. Typically, this is fine within a data center because the latency would be in the order of microsecond or sub-millisecond at most. And as a result, the idle period will be really, really small. The response from the worker would go back really quickly, and the coordinator will dispatch another task for the worker to do. And this idle amount will not, at the end of the day, amount to anything. It turns out that when you run interactive analytics, data is distributed across multiple silos, and the network has very high latency. And you are moving from the sub-millisecond data center network to hundreds of millisecond network between these silos. Your interactive tasks they can run on average 5 times slower or more. And it turns out when the computation you are trying to do is really small, maybe tens of milliseconds, and your latency over the network is hundreds of milliseconds, you spend more time just orchestrating and communicating commands in the control plane than actually doing any work. And it's not just the latency that affects. Bandwidth also impacts when we have long computation. So in this case, again, we have central coordinator and we have worker time going down, and then maybe we are training a model and we are sending updated model or updates to the worker, and then worker is doing some computation and sending back updates that are being aggregated and sent back to the worker again. And the reason in this case, the worker is idle for a long, long time, not because of anything other than the fact that there can be multiple workers in a silo, and all of them are, or many of them are competing for this scarce bandwidth that's coming into the silo. And as a result, you only need few workers worth of compute or CPU to actually saturate the available bandwidth. Everyone else is just waiting, doing nothing for the download to finish. And as a result, we found that if we, in the similar setting as before, if we do machine learning training, between these two types of network as we move from a 10 gigabit per second network to a 1 gigabit per second network, and everything else remains the same, even the latency. The completion time of these training jobs became 3 times worse. So both latency and bandwidth, they have significant impact on how long things take when we are trying to run things in a cross-silo setting, and actually to some extent even cross-device setting in any distributed setting, not simply because our bandwidth is low, it's taking forever, but because of low bandwidth and high latency, we end up with compute idling. Our compute can spend a lot of time being allocated but not doing anything, and which adds up really quickly as you do longer training or you have very high throughput cluster with many jobs being submitted where these idle periods could have been given to some other job to do some other computation. So Sol in one slide does 2 simple things. One is, as you can look, that I have spread out the central coordinator from the worker. It introduces this notion of a silo manager to decouple this slow network domain from the fast network domain. So on the left-hand side, we have this high latency, low bandwidth network over the WAN, wide area network. And within the silo, where workers are talking to the silo manager right now, instead of directly talking to the central coordinator, we have this typical cloud and high performance cluster setup. And what Sol does, where actual sort of innovation comes in, is figuring out from the central coordinator how many tasks to be pushed and queue up in the silo. So whenever a worker is done working on whatever it's working on, it doesn't have to wait too long, and it can get the next task and get started really quickly. And this is to make sure that we can sort of not bottleneck on worker waiting for new work to be done from the coordinator. On the worker side, instead of assigning a worker that is going to do the computation and then also do the communication where it has to upload and download all this big data, model, whatever, we rely on workers that are serverless. So your compute and communication within each worker is also decoupled. So there is a pool of workers, be computation work, but work can also be communication work. This is simply because right now, or before Sol, what we used to have is all the workers, they all have to do computation and communication. So when they are all contending with each other to communicate, their CPUs are basically sitting idle. And by decoupling using this serverless framework, now compute can be used while communication is actually going on. And in the process of doing this, we have to address many challenges that I'm not going to talk about. But one of the interesting things that my student fan who did the work is figuring out how do you push sort of just the right number of tasks to a silo. Because if you push too many and that silo for whatever reason goes down, then you have to rebalance, which may take a lot of time. If you push too few, then your workers have to idle, which is not efficient. So there's a lot of details in the paper, and that tries to take advantage of all these techniques that we have developed. And then what happens is we deployed Sol on 10 silos over the entire world. These are real machines running across the entire world. And we compared against the Spark baseline, which was designed for a single cloud. And we run standard analytics benchmark, TPC-DS and H, and we run machine learning benchmark that are non-neural network, sort of traditional machine learning, logistic regression, and so on and so forth. And we found that we get improvements that ranges from 4x to 16x, and we get about 2x improvement in overall utilization of all the compute that we have distributed over the world. And more interestingly, these allowed us to do sub-second interactive analytics of very complex SQL queries. It's not just simple scan over the data, but it's a complex query with many, many stages and many different operations to be performed across silo that are far, far apart over the world. So that's great. But then we started looking into cross-device scenario where the additional challenge is we have all these devices that are distributed, they are unreliable. They can go offline in any point in time, and I don't have to stress on it because we already had a very good intro on it from a real deployment. And some of the challenges, among others, we have to deal with is these extremely heterogeneous data and heterogeneous device capabilities, very large scale, and more importantly, this uncertainty. And as a result, most of the existing solution, they would pick clients somewhat at random, and across iteration, they would hope that thing could work out. So ART is a very recent paper we had in OSDI a few months ago, where Fan, again, he sort of started looking into how does random client selection affect the performance of federated learning. And there are two aspects. Of course, one obvious aspect that all of us are familiar with by now, that it takes a while to train. And because of heterogeneous devices, we can end up with stragglers. I mean, some of the solution would be overcommitting, as Hubert was mentioning earlier. There are many other approaches. The other thing that we found very interesting is that, and actually that came up during discussion yesterday during the breakout session, is that when the developer want to test sort of their model, it takes a while for them to actually see the results in the wild. They may want to test on a representative distribution, a representative sample of the overall population. It's just not easy to do that. So in this plot, what it's showing is that we trained the MobileNet model on the open image data set with 1.6 million images and 14,000 clients. We picked 100 per round that were randomly selected as defined by these standard algorithms like FedYogi and FedProx. And they took about 300 to 400 rounds and to achieve final accuracy of around 75%. And then we did a very unrealistic sort of comparison, that we have a centralized training that have access to all the data, a lot of resources, and then we train. And what is the highest level of accuracy we can get, which was much higher than what we got with federated learning. And it was much, much faster. And of course, all of this thing is expected because it's sort of an unfair comparison. You can go over all the data all the time. Everything is accessible. No one is unreliable. But still, it shows that there is this massive gap between what we can have and where things could be if we could somehow get there. Number of rounds taken for a target accuracy for different algorithms. So centralized one is the orange, and the black one is FedYogi plus random. I just picked one at random. In the paper, we have a lot of other data. They are all somewhat similar. In the y-axis, we have average round duration. And these two axes sort of represent the statistical efficiency and the systems efficiency of the training process. So what ART does during training is it works in two steps. First, over time, it exploits high statistical utility clients, and it tries to increase the statistical efficiency of training. And among those very high utility clients, it tries to prioritize high system utility clients that are likely to run faster. And by doing that, it improves the system's efficiency of training. And on the aggregate, what we found empirically is that the same algorithm, instead of just randomly selecting in every round, by using ART, we could train the model much faster and came much closer to whatever we could do with centralized training with a lot more resources spent. So FedYogi plus ART spends the exactly same amount of resources that FedYogi plus random selection is doing. And the same goes for FedProx plus ART versus FedProx plus random and FedAverage and so on. We have those data in the paper. And it turns out that by doing that, we can actually significantly improve the efficiency of federated training. And in the process of doing that, again, that I'm not going to go into too much details of, is that we had to address a lot of challenges in terms of which clients would we select to improve statistical efficiency. We may not even be able to go over all the clients to find the best ones. How can we trade off these two types of efficiency? The ones that may give higher loss may actually be slower, and ones that may be faster may not very useful in terms of improving statistical efficiency of training. So what we do is that we sort of enable the user of the system to define some parameters that allows them to navigate this trade-off. There are other challenges in terms of how can we avoid stale information. Maybe we have selected a client once and then many rounds have been passed. Maybe the next day we select it again, and the information that we have seen the last time that we were hoping to exploit in the next round, they have become stale. So we talk about how can we sort of avoid using stale information. And another challenge is because we are prioritizing both highly efficient clients in both direction, how to make it robust against noise? Is it possible to someone to introduce a few clients that give that are very fast phones, and they also have data that are probably made up but gives very good sort of loss characteristics? Would they be selected again? So we limit how many times a client or phone can be selected. And by applying all of these things, this is just a very small subset of the results. We are comparing FedYogi with ART versus FedYogi with random. And the numbers we care about is this 3.3x. So training MobileNet on open image data set, we could train 3.3 times faster to achieve the same target accuracy. And as we allowed it to train further, we actually received about 10% higher accuracy than whatever we could do with sort of vanilla FedYogi implementation. And the other part in gray here is that in both fronts, we saw improvements. Each of the rounds on average finished faster by using ART, but also the number of total rounds also decreased. So by improving in both fronts, we gained this overall improvement. And this is not just for this one task, sort of CV task. We have also tried out data sets such as Stack Overflow that people have mentioned before, but slightly bigger data set from Reddit on Albert, and it's even better. And in some other cases, it's not, I guess, as big of an improvement over the vanilla versions, but still we achieved some improvement both in terms of accuracy and total overall training time. So in the process of working on all these different projects, and there are too many, sort of this observation that every time we are trying to build these systems, eventually we need some workload that we want to train on and evaluate our systems on and compare against others. And many of the benchmarks, and there are at this point way too many, and I know we are creating one more, they often lack systems details. There is no information about what type of network they are running in, what is the network latency, what is the bandwidth characteristic. There is no information about what type of devices and how heterogeneous they are. Of course, maybe we do want to simulate them on GPU so we can run things faster, but we still want to emulate phones with many different characteristics that Hubert pointed out, that having this runtime on the end devices is very tricky. I mean, even before there, like the numbers we are seeing in all these research papers is very hard to sort of tell whether they are going to hold when you throw them into the wild. And then also there are no details about how much cloud resources on the aggregator side they have and how they're organized. Similarly, most of these data sets we found them to be awfully small to do any interesting systems research. And there were no traces of when the clients would become available. So we started with getting all the data set that exist in all these different sort of benchmarks and keeping the ones that we found that are pretty big. Then we added a lot of data set. I will get into that. But more importantly, which I think is unique, is very interesting, and which is something that FedScale adds to the community, is we collected these traces, not collected by us, from other sources in different communities of network bandwidth distribution across mobile devices, computation speed distribution across many, many mobile devices, and also traces of client dynamics, how long they stay connected, how long they remain disconnected. For example, the plot on the bottom right is showing this typical diurnal pattern on average, like clients are charging and discharging, and this many clients are available and these are not available, and so on. And of course, when you dig deeper into these traces, you will see very interesting characteristics and behavior, which allowed us to work on many interesting problems that are still sort of ongoing, and I'm not going to go into the details of. But the high-level point is, once you plug in this type of systems traces, many of the algorithms that you read and you think that the theorems make sense, their results don't look like sort of what they appeared in many of the small-scale experiments they have done. Similarly, on the dataset size, we have been collecting a lot of dataset and is continuously increasing. At least in some cases, for example, the Reddit one that I used, and in comparison to Stack Overflow, this one has 5 times more number of clients and many more sort of data points, and we could run at scale. And when we started running at scale, we ended up with this challenge where the state-of-the-art solutions were sort of couldn't run more than a few clients per round. So then we extended our runtime from ART and basically created a superset that is very extensible and general, that is fed scale runtime, FAR, that can scale to up to 10,000 clients per round. And in this case, everything is running on 10 GPU cluster, where we are simulating 10,000 clients per round, and we are comparing against a state-of-the-art solution, which basically sort of dies when you put 100 clients per round. And in the process of doing that, we are discovering many sort of nuances of very well-known algorithms, and eventually we hope to discuss all those results as well. So our end goal is to create this federated runtime and data sets and benchmarks and metrics that spans both cross-silo and cross-device and federated learning and analytics, so that people can quickly do things, but do things at a scale and in a setting that is much larger than they could have done in the past. So in conclusion, I'm just going to end up with sort of pointing out sort of the way I see it, how systems people can contribute. One is there is systems research. This is a great opportunity to rethink the entire stack many times over, to make them network aware and heterogeneity aware and adaptive and handle uncertainty and stragglers and so on. But there is also a room to provide community where we want to provide this very easy to use system that can provide faithful representation and that are fast and scalable, and that will allow our colleagues to sort of actually evaluate their algorithms and great theories on more realistic setup, and then see how they are going to hold up as they get, closer to being deployed to real world environments. And all these works have been done by way too many people. The one in orange are actually whose work I presented, especially Fan, who basically led and is leading all of our federated learning and analytics work. He is going to be in job market, not this cycle, but the next. And everyone else, I would also like to thank them for their many contributions in improving our work in a variety of ways. With that, I'll be happy to take questions. Thank you.
Yeah. Thank you, Mosharaf, for this inspiring talk and spearheading systems work in the community here. We do have a question from Saurabh in the chat, if you can see that, Mosharaf. And others, please feel free to type questions into chat.
Okay, thank you. So the FedScale benchmark work that your group and Harsh has presented at the recent Resilient FL workshop is welcome effort in this space. Upgrade leaf benchmarking effort from Amit's group at CMU. Questions is, what are open questions left beyond FedScale? I think it's less of having open question, is more about sort of having completeness. All of those benchmarks and many different systems, including FedML and FedEval and Flower, they are all great efforts. And I think one of the things, this is something I think we'll discuss during the end, is that we have these different groups. They're coming with different backgrounds and focusing on specific aspects. And it's not that they don't care about it, it's just that we think in terms of how to scale it up and scale it out. And that's why we were looking for this bigger data set. and we wanted to do it. And we are sort of, we actually had a very nice conversation with the FedML folks yesterday, and we hope to all of us somehow trying, I guess, getting the band back together, or getting the band together for the first time, to try to take an effort where we sort of organize these things and have very well-defined scenarios like TTC, where every query is well-defined and that exercises different aspects. And then when you evaluate it, you can actually get a sense of where things perform better and where things perform well. So I would say the next step would be some notion of having a standardized set of scenarios and setting and data set, so that you can say this is scenario 61, and then that's what you are optimizing on, and everyone can do apples to apples comparison without having to figure out hyperparameters and other things.
Great, thank you.
So,
there's one more question from Xiaoyang, and after that we probably have to switch to the next agenda item.
Yeah, so so what is Fed Yogi? Is it a variant of Fed OPT? I'm curious to know why this specific algorithm is chosen. So the way we started, because we are not machine learning expert, we were looking around and we were looking at what is the state of the art. I happened to attend the last year's Federated sort of workshop here, and some of the algorithms that were sort of well presented, we found that FedProx and Fed Yogi and a few others that are used by most of the machine learning researchers, and we started from there. Our framework is flexible enough to actually implement sort of Fed OPT or any other algorithm. In fact, we have recently implemented DPSGD and other variants of that that focuses on this privacy in our Fed scale framework, and we can try out sort of any of them. And actually all of everyone is welcome to sort of contribute back to this framework so that we have those implementations. So could you further introduce how do you align each client system trace with the synthetic partition data using in OpenImage? For image, I cannot get how to match the client that is more or less data points, those we have higher and lower bandwidth computation speed. This is a very good question and is a big challenge. We are working on it. There is no right answer. So what we've been trying to do is trying out many different combination and permutation of assigning clients with different type of traces. This is what we were discussing yesterday, by the way, when we had the breakout session, is that these traces we are collecting just to get a semblance of realistic setup, but they are coming from different sources, and it's unclear whether we should even try to mix and match them. But it's something about it, and this is only our first attempt, and we would like sort of everyone's input to make it more realistic and better and more accurate to what we see. And on that note, I would invite Google and all the big companies to think of what type of data set they can make available so that we can get this realistic flip behavior. And I think Hubert is already commenting is very difficult and complex. So, but we still need to, I don't know, try, Hubert, to come up with some simple thing that academics can still, I don't know, base their work on, so that they will come up with a really great theorem, and then it gives it to you, you run it on your platform, then you say, okay, it's a very good algorithm with a lot of bounds, it doesn't work. No, I mean, that's very disappointing for someone who is building theory. At least that's how I think, and I would guess everyone wants to have their work used in practice, and they would be heartbroken, no? I mean, if they don't get even a chance to, I don't know, figure it out, or not all of them can afford to come and, I don't know, spend a lot of time at Google to work with you to figure things out. And is this system deployable? I'm very interested in knowing your perspective on the edge runtime engine. This is another very good question.
A very quick answer on that point.
Yeah, so it is tricky, as Hubert pointed out, is one of the hardest thing. Several of my students are working, I don't know, very, very hard, and they have ended up with the same conclusion as Hubert, that you can't really support today the whole runtime, so you have to simplify it, cut it down, and then that limits what you can or cannot do. But there's a lot of research opportunities. And I would like to actually talk more about all of these things, so feel free to ask questions on the chat or just find me, drop me an email. I would love to jump on a call. Thank you so much again for the opportunity. Yeah, I mean, it's been a great workshop, and it's great to know about all the progress in federated learning and analytics.
Yeah, thank you, Mosharaf, for this exciting talk and sharing your work here.